Hello, my friends. We're going to convert between the equilibrium constants for pressure and concentration, Kp and Kc. I'm going to show you how the equation is derived and go through some real exam problems. So our first one here, this is a real exam problem. I just cut out all the words that we don't care about. It's calculate Kp equilibrium constant for pressures, using pressures, I should say, at 298 Kelvin for the reaction. And here's our equilibrium reaction, and we're given the equilibrium concentration, equilibrium constant for concentrations. Now we're gonna use this equation, it's the shortcut, but I'm going to show you where it comes from. Let's set up what the equilibrium constant for Kp is. So Kp is products over reactants. That's what equilibrium constants are. They're products over reactants. And for the products, we have, because this is for pressures, it's the pressure of NO squared, because we put this number to the power. And that's going to be times the pressure of Cl2 squared. Actually, I'll get rid of the parentheses so it doesn't look too messy. No, not squared. Never mind. There's no 2 there. And divided by the reactants. And there's only one reactant, so it'd be the pressure of this reactant. And we can only use pressures if these are gases. If they're aqueous, we can't use pressures. And if they're liquids and solids, we don't include them in the equilibrium constant at all. Okay, of NaCl, and that's squared here. Now, how do we get to Kc? Well, we use the ideal gas law that says that PV equals nRT, and we can solve for the pressure. Pressure equals nRT over V, and this N over V, this is our concentration, right? P equals, so this is like our concentration. I'll just say N over V because this is molarity, moles over liters, times RT. So we're going to plug that in to here, what this is here. So every pressure is now N over V RT. But rather than say N over V, I'm going to say this is the concentration of each species. So if this is for NO, this would be the concentration for NO. So we'll say this pressure here is the concentration of NO. Oh, I'll put it in. I'll keep it in blue. Concentration of NO times RT. And all of this is squared. And then next we have the concentration of Cl2, RT, and that's not squared, all divided by the concentration of NaCl times RT. Okay, now here we can simplify this, but I'm going to put these exponents to, I'm going to include this 1 here. Just there's a reason I'm doing that. Just so you can see where the equation comes from. So when we simplify this, we see that we have, we'll put all the concentrations together. So we'll put the NO squared and the Cl2, and that is to the power of 1, all divided by the concentration of NaCl to the power of 1. And then these RTs become RT, and it's going to be the power of 2 plus 1 minus 1. Do you see that? Let me know if that's confusing or not. But see, we have this RT term here, or factor, in all of them. And when we multiply exponents with the same base, or powers, when we multiply powers with the same base, we add the exponents. So 2 plus 1. And when we divide powers with the same base, we subtract the exponents. So 2 plus 1 minus 2. And this 2 plus 1 minus 2, this is the change in moles of our balanced chemical reaction. 2, here's our 2, plus 1, here's our 1, minus, oh, wait, there should be a squared here. Squared, this should be squared. Minus 2. This is squared, so this needs to be squared. So this needs to be squared, and this needs to be to the 2 here. So this is to the change. This is our change in moles here. This 2 plus 1 minus 2, and this part, this concentration, this is products over reactants. These are the products. This is the reactant here for using concentration. So this is literally our equilibrium constant Kc. So this whole thing, Kp, this is what Kp is. Kp, we're writing products over reactants. Kp is, I'll give myself a little bit more room. Kp equals Kc, which is this, times RT, change in moles. And this is our equation here, and this is the equation that you see up on the right, top right over here, and this is the one we plug in to convert between them. So I think we know what Kc is. Kc is 1.7 times 10 to the negative 2. 1.7 times 10 to the negative 2. R, we want to use this one, 8.314. Not joules, well, it is joules, but liters bar per mole Kelvin. Honestly, the units don't matter. I rarely say that, but they don't matter because our equilibrium constants are always unitless. Now, we don't want to screw this up. You want to make sure this RT is all to the power of this delta n here. So this would be 2 plus 1 minus 2. So that's just to the power of 1 here. So all of this is to the power of 1. Okay, we'll plug that into our trusty calculator. I think I did that already. 1.7 times 10 to the negative 2 divided by 8.3145 times 298 equals 6.9 times 10 to the negative 6. 6.9 times 10 to the negative 6. So that's our answer for Kp. So this is the equilibrium constant, products over reactants by looking at pressures. And this is the equilibrium constant by looking at concentrations. Okay, so you don't have to derive this every time on an exam unless you're asked to do that. Usually if you have an exam question like this, again, I cut out all the words that we don't care about, just gave you the stuff that you need. You can literally go straight to this equation, but do write the equation when you're writing your exam, because usually there's part marks that pertain to just writing out the equation. I haven't seen any profs not give part marks for at least writing the equation. Let me know if I'm wrong, if there are profs out there that don't give part marks for the equation. But anyways, it's good to start with the equation. I think so. 8.314, what is this? Liters, bars per mole Kelvin. And the temperature is 325 Kelvin. Make sure this is always in Kelvin. If it's in degrees Celsius, you need to convert to Kelvin. And all of this, I'm going to change the color just so it's super obvious, over the change in moles. Change in moles is going to be products over reactants, or sorry, products minus reactants, because it's a change. Products minus reactants, which makes sense because it's like final minus initial. This is like the final, this is like the initial, sort of, which is 3 minus 2. 3 minus 2, another 1. This usually isn't 1, but I guess for us it is. Okay. So we'll plug this into our calculator, 4.8 times 10 to the power of negative 9 times, and remember, all of this has to be in brackets, times 325, and that's to the power of 1, which I'll just leave it. Everything is to the power of 1 if we don't include it. Okay, so 1.3, is it 2 sig figs? Yeah, 2 sig figs here. So 1.3 times 10 to the negative 5, 1.3 times 10 to the negative 5. There's Kp. Right on. Okay, well, I hope this is getting pretty repetitive because repetition means good grades. We're just going to use the equation the other way. So we're going to calculate Kc now for this at some temperature for this equilibrium reaction if given Kp. So we'll write out the equation because it's always good to start with that. Try and do less steps in your head. That's my motto anyways, because I usually get it wrong if I try and do too many things at the same time. This is RT delta n. Now you also might see this as, rather than writing it as a fraction, as Kp times RT to the negative delta n, because this negative just means it's in the denominator. These are literally the same thing. Kp is 5.9 times 10 to the negative 5. R is 8.314 liters bar per mole Kelvin, although the units don't matter at all. 300 Kelvin, we want to make sure we're in Kelvin. And we want this whole denominator to be products minus reactants, which is, so delta n is going to be 3 minus 1. So 2, a different number, finally. All right, let's plug this in. Okay, so we got 5.9 times 10 to the negative 5 divided by 8.314 times 300, which is in Kelvin, to the power of 3 minus 1, which is 2. And so it says 1 times 10 to the negative 11. This gives us 1 sig fig, but we need to use our brain. We know that there's 2 sig figs here, so we're going to say it's 1.0 times 10 to the negative 11. So 1.0 times 10 to the negative 11, which is our K or KC. Sweet beans. All right, y'all. Hope you enjoyed it. Thanks again for watching, and I'll see you in the next video. If you got some value from this video, consider giving it a like. And yeah, thanks again. See you in the next one. Cheers.